Our guest videographer is Gavin today.
You want to show yourself, Gavin?
No.
So we'll see what sort of a... Okay, hey you guys, I need to teach you about one more difficult example of conservation of angular momentum. And here, let me just get this so it's not so taut. Oops, I did it, huh? Did it turn off?
No.
Oh, that's a miracle. Is it still recording?
Yep.
Okay, that's a big miracle. Okay, so I need to teach you two things before I can even talk about this harder conservation of angular momentum problem. Number one, you need to see what the relationship between angular velocity and linear velocity is, and then you need to see that something moving in a straight line can actually have angular momentum. It's kind of freaky, so let's get started. First of all, a relationship between omega and v. Okay? Here's the thing. You know that theta equals s over r. So there's a relationship between angular displacement and linear displacement. Angular displacement equals the linear displacement divided by the radius of whatever circle it happens to be rotating in. Okay? Well, if you're in calculus, you'll understand what I'm about to tell you. If you're in calculus, I could take the derivative of both sides of this equation with respect to t. Well, what's the derivative of theta with respect to t? What's the rate of change of theta?
d theta over d.
Good, d theta dt, but what else do we call d theta dt?
I have no clue.
No one knows what the rate... Okay, let's say you're not in calculus. Then it turns out since theta equals s over r, I can say delta theta equals delta s over r, and then I can divide both of them by t, delta t, so I get delta theta over delta t equals delta s over delta t over r. Well, what is the change in angular displacement over time? What is that? Thank you very much, Fatima. Angular velocity, right? Yes. Paul.
What's the derivative?
Sean. What? Are you in calculus? Then it is not for you to know. Yeah. But if you're not in calculus, at least you can see this. And I hope you see that the rate of change of theta has a relation, with respect to t, has a relationship with the rate of change of the arc that you've traveled in with respect to t. And that relationship is omega equals v over r. And there you go. That's huge. If I've got an object, and I don't care what that object is, and that object is rotating about a certain point, then if I looked at the velocity at any point on this object, the linear velocity, the tangential velocity, because it's rotating in a circle, so at any point the velocity is always a tangential velocity, the velocity at any point on this object, even on the interior of the object, the linear velocity of any point on this rotating object is going to be a tangential velocity. It's going to be tangent to the circle of rotation. You see, this point is rotating in a circle, and the linear velocity is necessarily tangential. Well, there's the relationship. Omega equals v over r. And that ends up being a really good, useful relationship to know. Not only does theta equals s over r, but omega equals v over r for something that's spinning, something that's rotating. Now, it turns out I could take another derivative. What do you suppose the derivative of omega is? For those of you, say again?
Alpha.
Thank you very much, Logan. Yeah, the derivative of omega ends up being alpha. And what's the derivative of velocity? Yeah, acceleration. So we get an additional relationship. We get alpha equaling acceleration over radius. But the only thing that's kind of tricky about this is now that we're talking about acceleration, there's actually two types of acceleration happening here. If this thing is spinning faster and faster, then you're getting a bigger and bigger change in the tangential velocity, and that ends up being the tangential acceleration. Okay? If your object is spinning faster and faster, then the instantaneous tangential velocity is getting bigger and bigger, thus meaning you have a tangential acceleration. But there's another thing happening here. If something's moving in a circle, what other type of acceleration does it have besides tangential acceleration? Yes, centripetal acceleration. So you end up having two types of acceleration. Tangential, which happens when you're going faster and faster or slower and slower, and then centripetal acceleration, which makes you move in a circle, which happens because you're moving in a circle. And centripetal acceleration is always directed toward the center of the circle. Tangential acceleration is always directed tangent to the circle. Well, guess what? In high school physics 1, we do not have to deal with this issue. It's fun, it's big fat fun, but we don't have to deal with it. But boy, oh boy, you do have to know this guy right there. You have to know the relationship between omega and the tangential velocity, and it is omega equals v over r. Well, that's the first thing you need to know. Now let's go ahead and do the example we're about to do. Here comes example number 1. Imagine I have a rod, and this rod is free to rotate frictionlessly about that point. So it rotates about that point, okay? Let's say this rod is 1.5 meters long. And let's say the moment of inertia of this rod happens to be 50 kilogram meters squared. Okay? I've got a ball, a 2 kilogram ball, and this 2 kilogram ball is going at a velocity of 10 meters per second. That ball's going to hit the rod, hit, and that ball's going to stick to the rod. So now, this rod, which had been at rest, is now, oh shoot, what an ugly rod. Here's a second. Oh well, that's not that much better, but so do you see the ball has stuck to the rod, and now the ball and the rod are rotating together about that point of rotation. Do you understand the scenario? And the question is, find the final omega. Find the final angular velocity of the system after the collision. Well, here's the problem. I don't get to do conservation of linear momentum. I've got linear momentum here, but after the collision, these things aren't moving in a line. I don't get to say momentum equals mass times velocity, because this guy's not moving in a straight line. It's rotating. So I don't get to use conservation of linear momentum. I don't get to use conservation of angular momentum, because although this guy is rotating, this guy isn't. This guy's moving in a straight line. So how am I going to solve this problem? And the answer is, like I said in the, I'll talk to the camera, like I said in the introduction, it turns out that an object moving in a straight line does have an angular momentum. And we're going to find what that is now. Okay? Angular momentum of a ball. I'll just say it's a ball, and it's any object, but I'm going to use the term ball to distinguish it from the rod. Angular momentum of a ball moving in a straight line. That's what we're about to find right now. Okay. This ball eventually is going to hit the rod. And this ball will be going 10 meters per second vertically right when it hits this horizontal rod. Well, this horizontal rod, he doesn't know that this ball coming at him was coming at him in a straight line. All he knows is that the ball is hitting him perpendicular to himself, which means, as far as he's concerned, this ball could have actually been moving in a circular path, right? This ball could have been moving in a circular path. And then when the ball comes around and hits this rod right here, hey, the ball's going in the correct direction, right? Tangent to the circle, vertical. And then they'll go in, then they'll go around and do their thing. So I just want you to see that this guy sees the ball as having rotation. This rod sees the ball as having an angular momentum. The only thing that's kind of tricky is, as far as the rod is concerned, his radius of rotation is the same as himself. The radius of rotation of that ball is 1.5 meters. So you get this weird situation that the radius of rotation of this ball moving in a straight line is determined by what it's about to hit. It's not determined by the ball itself, it's determined by what it's about to hit. It's about to hit something that's rotating at 1.5 meters, so as far as we're concerned, the radius of rotation of this ball moving in a straight line is actually 1.5 meters. So let's go for it. Angular momentum equals I omega. This is a point mass rotating at a radius r. Do you remember what the moment of inertia of a point mass rotating at a radius r is? Go ahead. That would be a disk. 1/2 mr squared is a disk. So how about for a point mass?
MR squared?
Yeah, just mr squared. Your favorite equation. Yeah, so we got mr squared. Great. And then times omega. Well, because he's moving in a circle and 10 meters per second is its linear velocity, I'm going to make this substitution. Omega is v over r. And now the r's cancel, one of the r's cancel, and I get mrv. And there it is. That's the angular momentum of an object moving in straight line motion, where m equals the mass of the ball, let's say. R is the radius of the rotation that the ball is about to acquire, which is weird, that the ball is about to acquire. And then v is the linear velocity of the ball. Alrighty, well then, hey, now that we have an expression for the angular momentum of a ball going in a straight line, we can solve the problem because we get to do conservation of angular momentum. So let's go for it. Conservation of angular momentum. Okay. My initial angular momentum is only contributed by this ball because this rod is at rest. So I got mRV. The final angular momentum, I have this inertia, the inertia of the rod and the inertia of the ball moving together. So I get to do what Noel and I were talking about earlier when we were going over homework. I get to just add those two discrete inertias. So I'm going to have the inertia of the rod plus the inertia of the ball multiplied by the final omega. Moment of inertia of the rod, moment of inertia of the ball. Okay, let's plug in. My ball is a 2 kilogram ball. The radius of rotation that the ball's about to acquire is 1.5 meters. and the velocity of the ball is 10 meters per second. The moment of inertia of the rod is given as 50 kilogram meters squared per second. The moment of inertia of the ball, I'm going to have to find that. The ball is still a point mass moving in a circle, so it's going to be mr squared, omega f. Let me see, 3, that's 30. 30 kilogram meters squared per second equals 50 plus m is 2 kilograms. And the radius of the circle that it's rotating in is 1.5 meters. Omega f. Hey, you're here.
I had to wait to get my backpack out of my teacher's class because there wasn't stuff.
Oh, silly son. Alrighty. And so now I got 1.5 squared is 2.25, twice that is 4.5. So I got 30 kilogram meters squared per second equals 54.5 kilogram meters squared times omega f. And so I get 0.55 radians per second equals omega f. Any question or problem on this? You guys ready to do one of these on your own? Oh, wait, before I ask you that, let me get a quick drink of water. Let me ask you this question. What if it turns out that the ball doesn't hit the rod at the very end? What if it turns out that the ball actually hits the rod at the 0.75 meter point? So this ball's gonna hit right here, and then the ball's gonna be smushed right there. How does that change the initial momentum of the angular momentum of the ball? Or does it change it? Yes, Fatima.
You would put 0.75 in the
Thank you. Remember, the angular momentum of an object moving in a straight line is determined by the radius of motion it's about to acquire, which is kind of weird. And this guy's going to acquire a circular motion of radius 0.75. So as far as the rod is concerned, it's already rotating at the radius of 0.75 when it hits it. So yeah, Fatima's right, this is 0.75. Someone besides Fatima, is something on this side of the equation going to get changed? Do I have to change the moment of inertia of the rod itself?
No.
Heck no. What's going to get changed?
The R.
Thank you. The R. This guy also becomes 0.75. Good. Hope you guys are okay with that. Yeah, freaky, freaky deaky. All right, well, here comes the problem you guys are going to do. I'm going to give you the very, very same problem in all ways, except instead of the ball sticking to the rod, the ball is going to bounce off and be going 5 meters per second down. And I want to see if you guys can clever your way out of this. So here's the scenario. Oops. You still got the rod. You still got the ball going 10 meters per second, okay? Everything's the same, hit. Except now, the ball isn't stuck to the rod. The ball's going 5 meters per second in the opposite direction. Please do this problem now. Find me omega f. And I'll walk around and help you. Yes, Noel?
Does it still hit at the 1.5?
Yes. Yeah, everything's the same. Still hitting at the 1.51. Still 50 kilogram meters squared for the rod, 2 kilograms, 10 meters per second for the ball. It's just bouncing off instead of getting stuck on. If anyone gets the right answer, I will fall over dead.
No, I'll get the answer wrong.
Nah, I'll bet a lot of people get it right.
Not really. It's the first time taking notes in like a week.
You know what I forgot to do? I forgot to pass these stupid things out. I'm gonna have you help me, because like 2/3 of these, like, didn't even Xerox. I don't know if you wanna separate out the double sided.
Yeah.
Oh, God, I mean, that wastes a ton of time. Okay, let's see how people are doing. Yay, the left side's correct. See if Tom Ritchie is correct.
Wait.
Hey, your left side's correct. Let me see what you get for the right side. Yeah, beautiful, you get it. You get it.
Yeah.
Good for you, Fatima. I see a correct answer in your future. Good, your left side's correct. Ooh, we're so smart, aren't we? We're so full of ourselves. We love ourselves so much.
I wish I was full of myself.
Okay, oh, so you treated them separately? Good for you. Oh, one more thing, by the way, the angular momentum of the 5 meter per second guy, do you think it's positive or negative? Oh, good for you. I didn't even have to say anything, you just got it immediately. Good. I want to tell you, you're going to have 2 separate and distinct angular momentums on the right side of that equation, because they're not stuck together anymore. Yeah, so don't do this. They're not stuck together anymore. They're 2 separate and distinct angular momentums. Yeah, don't do that. They're not stuck together. So you're just gonna have to have the angular momentum of the rod and the angular momentum of the ball totally separate from each other. Don't combine their lines, their rotational positions.
Should I just wait for him to do it? Yes.
See what's down the middle. You're treating yourself separately. Okay? 50 times omega.
So you don't have to use the MS.
Now, here's the thing, they're not stuck together anymore, so you can't combine them.
No,
like that.
No,
You're
that's
just
what
gonna
I'm
have to
saying.
have totally separate,
You don't have to do
the
the
angular
MS.
momentum of that guy plus the angular momentum of that guy.
Yeah.
Okay, yeah, don't do that, because they're not stuck together, so you don't combine their moments of inertia. They're 2 separate and distinct guys. Okay. Yeah, so it's gonna be 50 times omega f plus or minus whatever the momentum of that ball is after the collision.
Hmm? Hey, buddy.
So,
What's that right side look like?
yeah, you just call this MRP as well. That should work out. Oh,
So
minus
the-
and negative, don't do that, it's just minus. Don't have that like minus. Yeah, you'll be fine now, I think you're gonna get the right answer. We're just so in love with ourselves. On the right side of the equation, it's 2 different. The left side's the same. It's still not-
I don't know. I got 0.9. That's what I got. Chances are.
Hey.
Plus an MRV of about 5 meter per second.
Oh, what you put on the ball? Because it's not connected. See how it's not?
So you don't do the, you don't,
Together, it's 2 separate and distinct.
You know, oh, it's L, L stands for Indian or something. I never did that for the broad. The ball's not together. Is that what I mean?
Yeah.
Not
I wish
Pass
I
this out
did.
when I'm done with
Not me.
discussing.
oh, wait. No, I'm just gonna wait.
hopefully everyone started with initial angular momentum equals final angular momentum.
Yes,
But
sir.
I can't tell you what I finished with.
Okay, well, hey guys, let's do it. I saw what you're doing and everyone was doing it fine. On the left side is no different than it was before, MRV. But the right side, these two guys are not connected anymore. They are two separate and distinct entities. So each of them has their own angular momentum. You're gonna have the angular momentum of the rod plus the angular momentum of the ball. That's what you end up with here. You guys okay with that? Okay, before the collision, I've got a 2 kilogram object at a radius of 1.5 meters, going 10 meters per second, just as before. The angular momentum of the rod, well, it's gonna be the I of the rod multiplied by omega F, and then I get the angular momentum of the ball. And this is a ball moving in straight line motion, correct? So I'm gonna use MRV again. But here's one thing that's kind of weird. Notice, as far as this rod is concerned, this ball is moving counterclockwise, which means he has a positive angular momentum. What direction is that ball moving?
Clockwise.
Clockwise, right? He's moving clockwise. You know what I mean?
Yes.
And so, because he's moving clockwise, he's got a negative angular momentum. So I'm not gonna put plus there, I'm gonna put a minus here, and then MRV. You see that? And that's like one of the keys to doing this problem. So now I've got, what is that, 30 kilogram meters squared per second. I've got 50 kilogram meters squared times omega F minus 2 kilograms times 1.5 meters per second, whoops, 1.5 meters times 5 meters per second. And don't make that guy negative. I don't care. It's like when we were doing torques. I don't care what the direction of the force is. I only care whether I'm rotating the thing clockwise or counterclockwise. This guy's rotating clockwise, he gets to be negative. And so when you solve, you get omega F equaling 0.9 radians per second. How many people got 0.9? Okay, good for you guys. Good for everyone to raise their hand. Any questions or issues on this?
Yeah.
Now, can I ask you guys one question? You'll notice the angular velocity of the rod after the collision here is significantly higher than here. Here the rod is going slow. Here the rod is going a lot faster. Why is that? Yes, Fatima?
When the ball is sticking to the rod, then it makes the moment of inertia greater.
Okay, so Fatima's going, hey, I know about men jumping onto carousels. You know, you jump on the carousel, you increase the moment of inertia of the carousel, and the carousel rotates slower. This ball sticks to the rod, increases the moment of inertia of the rod, and the rod's going to go slower. But I want you to see something. How important is that effect? You know, like here, this mr squared, this ended up being 4.5. So I've got, oh, that wasn't a very good marker. So I've got a 50 kilogram meter squared object, rotational inertia object, that just got increased to 54.5. So yeah, it got increased a little less than 10%, but that doesn't account for almost doubling the omega. So there's something else happening here that is more important than just the increase in the rotational inertia of the rod. Yes, Imani?
Oh, I was gonna say, is it like that raindrop versus hail problem, where it's like the raindrop just like, and then the one that bounces is like more force when it bounces than.
Yes. You guys okay with that? That this is a raindrop and hail problem, and there's going to be more force exerted when something bounces versus when something goes splat? You guys okay with that? Because, well, remember with the raindrop and hail, what was increasing? When you bounced, what was bigger? Good, the force was bigger. Why was the force bigger? What other thing was bigger when it bounced? Yes.
Change in velocity.
Okay, change in velocity, but give me more. What else was bigger besides change in velocity? You're right. Yeah, change in, say again, Ezina?
Momentum.
Yeah, change in momentum. And do you remember what equals change in momentum? Yeah, impulse. I want to remind you that with the hail and the rain problem, we had impulse, which is force times the change in time, equaling the change in momentum. And when something bounces, there's a bigger change in momentum. And so a bigger change in momentum means bigger impulse, which means bigger force. Well, there is a thing which we don't learn about in our happy little class that you can call angular impulse. And angular impulse instead of force times time, what do you suppose that's going to be? What's that? Yeah, torque times time. And what's that going to be equal to? The change of what?
Angular.
Yeah, angular momentum. And so I want you to see by the ball bouncing, you get a bigger change in angular momentum, which means there's more torque being exerted on that rod, which means, you know, the rod's being hit harder, but I'm giving it more torque, and so it's going to rotate faster. You guys okay with that? I just want you to see that the ball bouncing off the rod, resulting in the rod having a higher omega, makes sense. All right. Well, hey, does anyone have any other comments? Well, just like I said, remember, if someone's going to hit you over the head with a bottle, do you want it to break or do you want it to bounce?
Break.
Yeah, you want it to break, absolutely, or you end up getting bigger force and bigger torque. Okay, well, go back.